Today, I Naveen are going to read a chapter from a book Inorganic Chemistry, Volume 3 by Pradeep Publications by Dr. K. Bhasin. Chapter 1 is Metal Ligand Bonding in Transition Metal Complexes. Section 1.4 Assumptions of Crystal Field Theory CFT. Crystal field theory is now more widely used in valence bond theory. It considers the attraction between the central metal atom and the ligand in a complexes as a purely electrostatic. The basic assumptions of the CFT are the following. First, the transition metal ion is surrounded by a number of ligands with the lone pair of electrons. Second, the ligands are treated as a point charge. The point charge are as electric charges that exist at a single point. It is important to remark that the point has no volume and no area. The ligand may be neutral, negatively charged species. In case of ligands are neutral, such as NH3, H2O, En, it is the negative end of a dipole that is oriented towards the metal ion that accounts for the electrostatic interaction. In case of negatively charged ligands such as chlorine negative, C2O4, 2 negative oxalate ion, cyanide ion, the interaction between the central metal atom and ion and the ligand is purely ionic, that is 100% ionic. All the 5d orbitals of ligand isolated gaseous atoms have the same energy. These 5d orbitals of gaseous atom possessing the same energy are called degenerate orbitals. If a spherically symmetrical field of negative charges is placed around the metal, all the 5d orbitals of metal will be raised in their energy as a repulsion between negative field and the negative charged electron of the orbital. In brief, energy of an orbital is raised because of a repulsion between the field and the electron on the metal. However, the energy of 5 orbitals will be remains degenerated. If the electric field results from an influence of real charges, that is ligand, either from a negative charge anion or ligand or a negative end of a dipole such as NH3, a neutral ligand, the electric field is not spherically symmetrical because of finite number of usually 4 or 6 ligands are involved. In such a case, the d orbitals are not affected equally by the electric field of a ligand. We also have noted that the d orbitals have different orientation in space and therefore these orbitals will experience different interaction from the ligand. The orbitals lying in the direction of ligand will experience greater repulsion interaction and consequently their energy will be raised. On the other hand, the metal orbitals lying away from the ligand will experience less repulsive interaction. As a result, their energy will be raised to a smaller extent. In a summary, the energy of 5d orbitals of metal are split up due to an electric field generated by ligands surrounding the metal. The splitting of energy of 5 degenerate d orbitals of metal ion into two different sets of orbitals into different energy in presence of electric field of ligand, that is crystal field splitting. Fifth point, the number of ligand coordination numbers surrounding the metal affect the energy of 5d orbitals. It means that the crystal field splitting is different with the different coordination number. Sixth, the property of the coordination compound such as magnetic property and color of a compound can easily be explained in terms of splitting of d orbitals in different crystal splitting. Section 1.5 Crystal field splitting in octahedral complexes. In octahedral complexes, the metal is at a center of octahedron whereas surrounding ligands are at 6 corners of the octahedron. Let us consider first the metal ion without any ligand surrounded in. In this case, all these 5d orbitals possess same energy and are called degenerate orbitals. This is represented by 5 lines at the same level of on the left. Mark state 1. Let us now place this metal ion in a spherically symmetrical field. Symmetrical electric field consists of 6 negatively charged ligands. The electron present Electron present in the metal d orbitals will interact repulsive with the electric field of a 6 negative charges. This repulsion between the like charges raise the energy of d orbital equally by some amount of as shown in figure. Marx stated it too. Let us now consider the electric field degenerated by 6 charged placed at vertices of an octahedron on a XYZ axis. It is important to recall that the total charge around the metal ion is the same, but it's disturbed in different hand. Hence, the surrounding charges is not a spherically symmetrical, and the inspection of a figure 1.14 shows that dz square and dx square minus y square orbitals point directly towards the 6-point charges representing the ligands. These two orbitals interact directly or strongly with the ligand charges. As a result of a strong repulsive interaction, their energies are raised, as in figure number 1.14. The other three orbitals, that is dxy, dyz and dzx, are not affected as much as compared to dz square and dx square minus y square. As a result of the energies, dxy, dyz and dzx are lowered as shown in figure 1.14. The relative to the energy of 5 orbitals in a spherically symmetrical field. It is important to note that the energy of dz square and dx square minus y square orbital are precisely be equal. It means that these two orbitals are degenerate. Similarly, the three orbitals, that is dxy, dyz and dzx, are also be degenerated. A close inspection of figure number 1.14 reveals that dxy, dyz and dzx orbitals are in an equivalent environment in octahedral geometry. It may be appears that dx square minus y square orbital is being repelled more by 4 ligands, or dz square is being repelled less by 2 ligands. It is important to recall that dz square orbital is a linear combination of dz square minus x square and dz square minus y square, and has also electron density in xy plane. As a result, both the dx square minus y square and dz square orbitals are equally affected and are degenerated. The pattern of one doubly degenerated and one triply degenerated orbital sets shown in figure 1.13 is characteristics of all these orbital complexes, octahedral complexes. The set of 3 degenerated orbitals is named as T2G, read as T2G. The origin of these names come from a branch of mathematics called group theory. The other set of 2 degenerated orbitals is named as EG, read as EG, as the origin of these names come from the mathematics called group theory. We have noted so far that in octahedral complexes the 5 orbitals are split up into 2 sets. One set consists of 3 orbitals of lower energy, T2G orbitals, and other set consists of 2 orbitals of higher energy, that is EG orbitals. The energy difference between the two set of d orbital is called crystal field splitting energy, and it is abbreviated as CFSE. It is symbolically designed as delta O. The subscription O indicates for that the complex is octahedral. The actual value of delta O depends upon a particular compound and varies with the metal ion, the ligand and the charges on the complexes. Some of these factors will be discussed later. Sometimes another parameter dq is represented instead of delta O, and these two parameters are related as delta O is equals to tan of dq. Let us now consider the approach of ligand as a two-set process. In first step, the ligand approaches to the metal ion and produces a hypothetical spherically symmetrical field which repels all these orbitals to a same extent. In second step, the ligand approaches to the metal and splits the orbital degeneracy due to the repulsion of different extent. It is important to note that the crystal field occurs in such a way that the average energy of d orbitals will remain same. In other words, the center of gravity of d orbitals remains constant during the second step. It means that decrease in energy of a set of orbitals that lies at a lower energy must be balanced by corresponding increase in the other two sets. Therefore, if the T2G set drops by 2 units, a balance is achieved if the EG set raised by 3 units. If the difference between the T2G and EG level is defined as delta O, then it is clear that the energy of T2G level changes by minus 0.6 del O, while the energy of EG set will changes by plus 0.4 del O, relative to a spherically field of reference point. In terms of 10 dq, in octahedral cases, the T2G level is stabilized by 6 dq, while EG level is destabilized by 4 dq, relative to a spherical field reference point. Next is 1.6 article, various DN configurations of octahedral complexes. We have discussed in section 1.5 that it is an octahedral complex. The energy of 5d orbitals are split up into two sets of degenerated orbitals via T2G and EG. The energy of T2 set is lowered, whereas the EG set is raised due to repulsive interaction with the ligand to different extents. The number of d orbitals present in a metal ion are to be arranged in T2G and EG energy levels of d orbitals. The constancy of pericenter of a d orbital is similar to the conservation of energy of the orbital. The unit del O is preferred over 10 decals as it states that the geometry of complexes and avoids confusion while discussing the other geometries for what a different value of crystal field splitting energy is used. Next, the D0 to D3 configurations. Here is the electronic configuration for D0 to D3 case are shown in given figure. If the electronic configuration of a metal is D0, then there is no electron in the d orbitals of the complexes. In case of D1 system, that is titanium plus 3, the d electron occupies the lowest available orbit. This can be placed in any of the T2G set. Since the electron occupies one of T2G set, it is stabilized by amount of equal to 0.4 del O. The relative to the energy of 5d orbitals in electric field is shown by dotted lines. Since the positive value goes upward to the dotted line and the D1 configuration is stabilized by minus 0.4 del O relative to the reference point. This stabilization is called crystal field stabilization energy. In the D2 configuration, example vanadium plus 3 ion, there are two sets. These two electrons will occupy the T2G orbitals, and therefore the spin parallel is accordance with Ahern's rule. In each of the electrons stabilized by minus 0.4 del O, so the total crystal field stabilization energy is 2 into minus 0.4 del O, that is equals to minus 0.8 of delta O. In the D3 configuration, example chromium plus 3 ion, there are 3 electrons to be put in a T2G set, hence goes on each orbital with the spin parallel. The crystal field stabilization energy is so therefore given by 3 into minus 0.4 delta O, that is 1.2 del O, negative minus key. Next is the D4 to D7 configurations. The filling of one of the three electrons in d orbital in case of octahedral complexes is very simple and straightforward. However, in case of d4 configuration, there are two possibilities. First is all the four electrons may be put occupies T2g orbital. Three electrons will occupy T2g orbital while the fourth electron have to spin pair up with any of the three orbitals occupies in the orbital. In such case, the electron configuration will be T2g4. In this case, there is an energy penalty to pay the pairing up the two electrons. This is a pairing energy. Second case is the three electrons may occupy T2g orbitals while fourth electron may go to their EG orbital. In such cases, the electron configuration will be T2g3 EG1. In this case, the extra energy is required to push the electron into the EG orbital over the dotted line as shown in figure, the reference point in the terms. In first case, the contribution to CFSE of fourth electron is given by minus 0.4 del O plus pairing, where P is a pairing energy. In second case, the contribution of CFSE for the fourth electron is given by 0.6 del O, that is destabilization. Our actual configuration can be decided on the basis of delta O. There are two unpaired electrons in first case and shown resulting energy level diagram. There are four unpaired electrons in second case. Since there are few unpaired electrons in first case than in second, where there are four unpaired electrons, the first configuration is called low spin and the other second configuration is called high spin. Next, the CFSE value for the D4 configuration as shown is in the low spin case. The overall CFSE is minus 1.6 del O plus pairing. In this high spin case, the CFSE is minus 0.6 delta O, assuming that the fourth electron has occupies another orbital. It is clear if the delta O greater than pairing energy, the complex will prefer to have a low spin configuration, and in case of pairing energy is greater than delta O, then the complex prefer to have a high spin configuration. This is shown in figure. The center part of the diagram represents the 5 degenerated orbitals in spherically symmetrical field. The situation of the left is shown low spin case for the delta O greater than the pairing. The situation on the right hand side, the high spin for delta O is less than pairing. It is important to realize that for D4 configuration, spherically symmetrical field, there is no unpaired electron. The in octahedral field, there is a low spin case. Two electrons are paired. Hence, the value of P must be included in CFSE calculation. In case of high spin, there is no unpaired electron. So, the value of pairing has to be included. Further, if delta O is large, the complex are called strong field complexes. On the other hand, if delta O is small, the complexes are called weak field complexes. Strong field complexes encourage pairing whenever possible and are therefore a low spin complexes. On the other hand, weak field complexes do not encourage of pairing, therefore they are high spin complexes. If delta O CFSE is greater than P pairing energy, this is only for strong field complexes, we get low spin complex. If delta O, that is CFSE, is less than pairing, then the weak field complexes, which gives high spin complexes. Similarly, in case of D5, D6 and D7 octahedral complexes, there are two possible correspondings to low spin and high spin. CFSE in case of in these cases can easily be calculated as shown. in figure number 1.16 and 1.17 respectively. D8 to D10 configuration. In case of D8 to D10 configuration, there is a nothing like high spin or low spin configuration. This is because if we assume the complex to be low spin, then first 6 electrons will be till T2G set orbital. Remaining 2 electrons will goes into EG, 1 electrons to each. If we assume the complex to be high spin, then first 5 electrons will go 1 in 5D, remaining 2 of would be filling in T2G set in both these cases, and result is the same. Thus, there is only one possible electronic configuration in D8. Similarly, there is a one electronic configuration possible in a D9 and D10 case. The crystal field stabilization energy for a metal with D1 to D10 configuration in weak and strong is summarized as given below. Next is article number 1.7, crystal field stabilization energy and CFSE for tetrahedral complexes. Imagine a metal ion which is not surrounded by ligands. All these 5d orbitals of metal in such a case have same energy, and this is represented by 5 lines lying at a same energy level on the left. In presence of tetrahedral field, degeneracy of 5d orbitals lifted up as first is 2 orbitals, that is dx square minus y square and dz square become stable and their energies will lowered to 6 dq. Second, the 3 orbitals dxy, dyz and dzx becomes unstable and their energies are raised by 4 dq. The crystal field stabilization energy in tetrahedral complexes can be calculated in the terms of algebraic sum of minus 6 dq per electrons in electron orbital and plus 4 dq for each electron in T2 orbitals. CFSE for tetrahedral complexes with the different number of metal d electron in terms of dq and delta T as shown in figure. The splitting of d orbitals in case of tetrahedral complexes are designed as E and T2 instead of EG and T2G. The subscription G is dropped because tetrahedral geometry has no center of symmetry. The symbol G is only used for electric field which has a center of symmetry. Next is tetrahedral complexes. Two of the most common geometries for 4 coordination complexes are tetrahedral and a square planar arrangement. A tetrahedral arrangement of 4 ligands surrounded by a metal ion can be imagined by placing 4 ligands on an alternate corner of a cube, or by placing the 4 ligands on the opposite corners of a cube. A tetrahedral complex can also be imagined by removing 4 of the 8 ligands from opposite corner of the tetrahedral complexes. Can also be imagined. The 3 coordinate axes are defined as passing through a center of a cube and the center of each cube face. In this arrangement, the ligand do not directly approaches and the metal d orbitals. However, the ligands comes closer to dxy, dyz and dzx orbitals that are directed towards edges of the cube as compared to dx square minus y square and dz square. Orbitals are directed to the center of the face of the cube. As a result, the energy of 3 orbitals, namely as dxy, dyz and dzx, labeled T2, will raise, whereas the energy of 2 orbitals, which is dx square minus y square and dz square, labeled as E, will be lowered. Thus, the T2 orbitals are destabilized, whereas E orbitals are stabilized. Further, since the center of gravity rule holds, T2 orbitals are raised for 4 dq and the E level lowered by 6 dq from the very center. The magnitude of CFSE, crystal field splitting energy, delta T, here T is for tetrahedral complex, is the difference in energy between doubly degenerated E and triply degenerated T2 level. The subscript T indicates tetrahedral complex. It is also measured in terms of dq or related to delta T. Delta T is equals to 10 dq. In tetrahedral complex, as mentioned earlier, the ligand do not approach any of the metal orbitals directly in the addition. Only four ligands instead of 6 or octahedral complex split the d orbitals. 4 ligand instead of 6 would be result 33% of decrease in field. Thus the split of d orbitals in tetrahedral is much more smaller than the splitting of octahedral complexes. It has been experimentally found that the crystal field splitting energy in octahedral is nearly more than twice as that of tetrahedral for the same metal ion and the same ligand. It has been found that the point charge model delta T will be equals to 4 by 9 of delta O. Since the crystal field splitting in tetrahedral is quite small, it means the pairing of electron not energetically favored. It's amount to say that the pairing energy P is virtually always greater than the splitting between E and TZ level. As a result, virtually all these tetrahedral complexes are of high spin complexes. Section 1.8, that is crystal field splitting in tetragonal and square planar complexes. If two trans ligands in octahedral complexes are moved either towards or away from the metal, the resulting complex is called tetragonally distorted. If the two trans ligands are brought closer to the metal, the octahedron tends to flatter. This is a flattening of octahedron. If two of trans metal ligands are shortened while other four metal ligands being longer, if two mutually trans ligands are completely removed, it results a formation of square planar complex. Since the octahedral is a symmetrical, it does not matter whether the mutual trans ligands are removed, but the axes from these ligands are removed in conveniently defined as z-axis. A partially removal of ligands along z-axis gives a distortion octahedron. As the ligand on z-axis are moved away, there is an increase in the metal ligand bond length along the z-axis. The increase in the length of a metal ligand bond decreases the repulsion between the ligand and the metal electron present in dz square orbital. As a result, the energy of d orbitals is decreased relative to that of octahedral field. On the other hand, if a metal ligand bond along x and y are shortened, the d orbital in xy plane via dx square minus y square feels greater repulsion from a ligand and therefore its energy is increased. On the similarly lines dz square, dxy and dyz orbitals are lowered in energy whereas dxy orbitals is raised. The splitting pattern in tetragonal distorted square octahedral complex is given in a structure given below. In square planar complexes, further the increase in dx square minus y square and dxy occurs with simultaneously decrease in energy of dz square and dxy and dyz orbitals as shown in a figure. It has been found that the energy of dz square orbitals falls below dxy orbitals in case of square planar complexes. Next is Section 1.9 Factors affecting crystal field parameter. There are a number of factors which are affecting extent of splitting of d orbitals by ligand. They are discussed given below. First point is nature of ligand. The crystal field splitting depends primarily on the nature of a ligand surrounding the metal ion. The greater the ease with which the ligand can approach the metal ion, greater will be the crystal field splitting. The ligand which cause smaller crystal field splitting are weak field ligands, and the ligands which cause larger crystal field splitting are strong field ligands. The ligands can be arranged in series of spectrochemical series. According to this, the increase in magnitude of crystal field splitting as shown in given below. A spectrochemical series, that is I negative, Br negative, Cl negative, SCN negative, F negative, OH negative, OX2 negative, H2O, NH3, En, NO2, Cn negative, CO. This is the order of increasing field strength of these ligands and also the increasing value of del O. Those on the left of NH3 are called weak field ligands, and those on right of NH3 are called strong field ligands. The order of spectrochemical series remains practically same irrespective of their transition metals. The effect of crystal field splitting delta O on the ligands attachment to the chromium 3 and cobalt 3 are shown in a table. A close inspection of table number 1.3 reveals that the order of ligand remains same irrespective of their metal. Second, the oxidation state of a metal ion. The magnitude of crystal field splitting depends on the oxidation state or a valency of central metal ion. The trivalent metal ion causes larger crystal field splitting than the divalent metal ion. For example, crystal field splitting in trivalent cobalt complex cobalt H2O whole 6 plus 3 is 18,600 centimeter inverse, whereas correspond to the divalent cobalt complex cobalt H2O whole 6 plus 2. The CFSE is only 9,400 centimeter inverse. The increase in crystal field splitting is due to the increase in a charge on a metal ion that tends to pull the negative charge ligand more effectively towards itself. An inspection of table number 1.4 reveals that trivalent metal ion displays a greater crystal field splitting than the divalent metal ions. Next is type of d orbitals. The magnitude of crystal field splitting within a same transition series as shown in table number 1.4 do not varies greatly. However, appreciably change 30 to 50% in crystal field splitting occurs on moving from 3D, that is first transition series, to the 4D, that is second transition series. Almost similar increase in crystal field splitting is observed on moving from 4D second transition series to the 5D third transition series. This can be readily seen from a table number 1.5. Fourth point, the geometry of the complexes. The crystal field splitting energy is, in case of tetrahedral complex, is less than the octahedral complex. This is because there are only 4 ligands in tetrahedral complex and there are 6 ligands in octahedral complex. In addition, there is a ligand along each axis on a octahedral complex, whereas no ligand lies directly along any axis in a tetrahedral ligand, any one axis. The split in octahedral ligand found to be somehow more twice than the stronger for a tetrahedral field for a same metal and a same ligand. Delta T is equals to 4 by 9 of del O. The splitting energy for tetrahedral complex is smaller as compared to pairing energy P. This explains that shows most of these tetrahedral complexes are of high spin. Section 1.10. Thank you.